One of the largest structures associated with our solar system may contain trillions of icy objects, stretching nearly halfway to the nearest star. Yet no telescope has ever photographed it. No spacecraft has visited it. No astronomer has captured an image of even a single object sitting at its most distant reaches. It is not hiding behind anything. It is not in some faraway galaxy. It supposedly surrounds us right now, enclosing everything we know about our solar neighborhood inside an invisible shell. So how can scientists claim it exists? The answer involves one of the most elegant pieces of detective work in all of astronomy. A chain of evidence built not from what we can see, but from what keeps falling toward us out of the darkness. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that should feel impossible. Imagine one of the largest structures associated with our solar system. Something that may contain hundreds of billions of icy objects, perhaps even trillions. Something that stretches so far from the sun that it reaches nearly halfway to the nearest star. And now imagine that no human being has ever seen it. Not a photograph. Not a faint smudge on a telescope image. Not a single confirmed detection of even one object sitting at its most distant reaches. This is the Oort Cloud. And the fact that scientists believe it exists without ever having directly observed it is one of the most fascinating examples of scientific reasoning in all of astronomy. When most people hear the word cloud, they picture something visible, white clouds drifting through Earth's sky, or the colourful nebulae in telescope images, glowing gas and dust lit up by young hot stars. But the Oort Cloud is nothing like that. It is not a bright, glowing structure. If you could somehow travel out to where the Oort Cloud is supposed to be, you would see absolutely nothing unusual. Darkness. Empty space stretching in every direction, with distant stars scattered across the sky just as they appear from Earth. You would not know you were inside the Oort Cloud because there would be nothing visible to tell you. The reason is simple but important. The objects that supposedly make up the Oort Cloud are tiny and incredibly far apart. We are talking about chunks of ice and rock, most of them probably only a few kilometers across. Some may be the size of a small mountain, others no bigger than a large building. And the space between them is enormous. Not just large, not just vast. Genuinely enormous, even by the standards of outer space itself. The average distance between two neighbouring objects in the outer Oort Cloud may be several billion kilometers or more. To put that in human terms, the distance from Earth to the Sun is about 150 million kilometers. Two neighbouring Oort Cloud objects might be separated by a distance tens of times greater than the gap between Earth and the Sun. You could travel for years at spacecraft speeds and never come close to encountering a single one. The Oort Cloud is not crowded, it is the opposite of crowded. It is a vast, sparse, nearly empty shell where individual objects are so widely scattered that the space between them dwarfs the objects themselves by factors of billions. And these objects are dark. They produce no light of their own, and they are not close enough to the sun to reflect much sunlight back toward us. At the distances we are talking about, tens of thousands of times the distance from Earth to the sun, our star would appear as just another bright point of light in the sky. Nothing like the blazing disk you see from Earth. The amount of sunlight reaching an Oort Cloud object at those distances is vanishingly small, and the amount that bounces back toward our telescopes is smaller still. Detecting one of these objects would be like trying to spot a single grain of dark sand floating in the Pacific Ocean from an airplane at 12,000 meters. It is far too faint, far too small, and far too distant to pick up against the blackness of space with any telescope humanity has ever built or is currently planning to build. So if we cannot see the Oort Cloud, if we have never photographed it, if no spacecraft has come anywhere close to reaching it, then how can astronomers claim it is real? How can they talk about it in textbooks and documentaries and scientific papers with any confidence at all? The answer lies in the comets. The Oort Cloud has never been seen directly, but it has been sending us messengers for as long as humans have looked up at the night sky. And those messengers are long-period comets. To understand what long-period comets reveal, you first need to understand what a comet actually is. A comet is essentially a chunk of ice, dust, and rock left over from the formation of the solar system roughly 4.5 billion years ago. When a comet travels close to the sun, the heat causes its icy surface to vaporize, creating a glowing cloud of gas and dust called a coma that can swell to enormous size, sometimes wider than Jupiter. The solar wind and radiation pressure then push some of this material outward, producing spectacular tails that can stretch for millions of kilometers across space. These tails are what make comets so dramatic when they appear in our sky. Ancient civilizations were both awed and terrified by them, seeing them as omens, as signs that something momentous was about to happen. For most of recorded history, that fear and wonder was all humans had. Comets appeared without warning, blazed across the sky for a few weeks, and vanished. Nobody knew where they came from, what they were made of, or whether they would ever return. They seemed to obey no pattern whatsoever. A comet might appear in any season, in any constellation, moving in any direction. To ancient observers, they looked like intruders, objects that did not belong to the orderly heavens of fixed stars and predictable planets. The Chinese called them broom stars because their tails swept across the sky like a broom. The Romans believed they signaled the death of rulers. In medieval Europe, a bright comet was widely considered a warning from God, a sign of plague, famine, or war. The first person to crack the mystery of comets was an English astronomer named Edmund Halley. In 1682, a bright comet appeared, and Halley observed it carefully, calculating the shape of its orbit using the gravitational theory that his friend Isaac Newton had recently developed. When he compared his results to historical records, he noticed something remarkable. A comet observed in 1531 had followed almost exactly the same orbital path. So had a comet observed in 1607. The intervals were roughly 75 to 76 years apart. Halley proposed that these were not three separate comets at all. They were the same object, returning again and again on a closed elliptical orbit around the Sun. This was a revolutionary idea. It meant that at least some comets were permanent members of the solar system, gravitationally bound to the Sun, traveling on predictable paths that brought them back to the inner solar system at regular intervals. Halley predicted that the comet would return again around 1758. He did not live to see it. He died in 1742. But on Christmas night of 1758, the comet reappeared exactly as he had predicted, a triumph of gravitational theory and observational astronomy that cemented Halley's name in scientific history forever. The comet has carried his name ever since. Halley's discovery solved one part of the puzzle. Some comets are periodic, They orbit the Sun on fixed schedules, returning to the inner solar system every few decades or centuries. Their orbits are elongated but closed, and their behavior is predictable once you understand the gravitational forces acting on them. They are not random intruders. They are permanent residents of the solar system, following paths that bring them back again and again like clockwork. Over the following centuries, astronomers would identify many more periodic comets, each one returning on its own schedule, each one obeying the same gravitational laws. But Halley's discovery also deepened the mystery in another way, because it immediately raised a question that nobody could answer at the time. If some comets return on regular schedules, traveling along the same path every 75 or 100 years, then what about the comets that do not return? What about the ones that appear once, blaze across the sky on an orbit stretching to unimaginable distances, and then vanish into the darkness never to be seen again within any human lifetime? Where do those comets come from? Why are their orbits so different? And why do they arrive from seemingly every direction in the sky rather than following orderly, predictable paths? These were the questions that would simmer for more than 2 centuries before Jan Oort finally assembled the evidence into a coherent answer. The periodic comets would eventually be traced to a relatively nearby reservoir in the outer solar system. But the long-period comets, the ones that arrive once and disappear for millennia, demanded something else entirely. Something much farther away. Something nobody had ever seen. But the solid part of a comet, the actual body called the nucleus, is usually just a few kilometers across. Comet Halley's nucleus, for example, is roughly 15 kilometers long and about 8 kilometers wide. That is tiny by any cosmic standard. It is smaller than many cities on Earth, and yet, when Halley approaches the Sun and its ices begin to vaporize, it produces a spectacle visible to the naked eye across tens of millions of kilometers of space. The nucleus is small, but the show it puts on is magnificent. Comets come in different varieties, and the key distinction for our story is the length of their orbits. Short-period comets complete one full orbit around the Sun in fewer than 200 years. Comet Halley, with its period of about 75 to 79 years, is one famous example. But the most numerous short-period comets are what astronomers call Jupiter family comets, with periods of less than 20 years. These tend to orbit in a relatively flat plane, roughly aligned with the orbits of the planets. They come from a region beyond Neptune called the Kuiper Belt, a disc-shaped collection of icy objects that astronomers have actually observed directly. We have found thousands of Kuiper Belt objects with our telescopes. We have photographs of them. We have measured their sizes and orbits. The Kuiper Belt is real, confirmed, and directly observed. It is not a mystery. But long-period comets are entirely different. These are comets that take more than 200 years to complete a single trip around the Sun. Some take thousands of years. Some take tens of thousands. Some take millions. Their orbits are so stretched out, so incredibly elongated, that they spend the vast majority of their existence far, far from the Sun, deep in the outer reaches of the solar system, where sunlight is barely a whisper. They swing inward, pass through the inner solar system over the course of a few months, put on their brief spectacular display, and then head back out into the darkness on a return journey that will take centuries or millennia to complete. Some have orbits so extended that they may never come back at all. escaping the sun's gravitational grip entirely after their one brief visit to the inner solar system. And here is the crucial observation, the one that changed everything and gave birth to the idea of the Oort Cloud. When astronomers carefully tracked the orbits of long-period comets, charting where they came from and where they were going, they noticed something extraordinary. These comets arrive from every direction, not from one particular region of the sky, not from a narrow band, not from a specific patch of constellations. They come from above the plane of the planets. They come from below it. They arrive from the direction of every constellation in every season. Their orbits are tilted at every possible angle relative to the flat disk in which the planets orbit. Some travel in the same direction as the planets, counterclockwise when viewed from above the North Pole of the solar system. Others travel in the exact opposite direction, clockwise, completely reversed. There is no preferred orientation whatsoever. The distribution of their arrival directions is essentially random, uniform, spread evenly across the entire sky. This is completely different from what we see with short-period comets. Short-period comets tend to stay close to the ecliptic, the flat plane in which the planets orbit the sun. This makes sense because they originate from the Kuiper Belt, which is itself a relatively flat disc-shaped structure sitting roughly in the same plane as the planets. Objects that come from a disk naturally arrive from directions close to the plane of that disk. But long-period comets show no such pattern. They come from everywhere. They arrive from above, from below, from the sides, from every angle imaginable. Their arrival directions are as random as raindrops falling on your head from an overcast sky. This single observation is the most important piece of evidence for the Oort Cloud. Think about what it means. If long-period comets arrive from all directions equally, then whatever reservoir is producing them cannot be a flat disk like the Kuiper Belt. A disk would send comets inward mostly from the plane of the disk, with very few arriving from above or below. And the source cannot be a ring because a ring would also send objects preferentially from its own plane. The only geometric shape that would send objects inward from every direction equally, with no preferred plane, no preferred angle, no clustering whatsoever, is a sphere. A sphere surrounds a central point equally in all directions. If you scatter objects evenly across the inside surface of a sphere, and then give random ones a nudge toward the center, they will fall inward from every direction with equal probability. That is exactly what we observe with long-period comets. The evidence points unmistakably toward a source that is roughly spherical, a shell of objects surrounding the entire solar system in 3 dimensions. There is another piece of physical evidence that strengthens this picture, and it comes not from the orbits of comets, but from their composition. When astronomers study the chemical makeup of comets, they find striking differences between short-period comets and long-period comets that are arriving in the inner solar system for the first time. Short-period comets have passed close to the sun dozens or hundreds of times. Each pass bakes their surfaces, driving off the most volatile ices, the compounds that evaporate at the lowest temperatures. After enough orbits, a short-period comet becomes depleted. Its surface develops a dark, insulating crust of dust and organic residue. It produces less gas and less dust on each subsequent pass. Some short-period comets eventually stop producing visible tails altogether, becoming what astronomers call dormant or extinct comets. Dark, inert objects that look more like asteroids than the spectacular visitors most people picture when they hear the word comet. Long-period comets arriving for the first time are completely different. They are pristine. Their surfaces have never been heated by a close approach to the sun. They carry volatile ices that short-period comets lost long ago. Compounds like carbon monoxide ice, frozen carbon dioxide, molecular nitrogen ice, and other substances that sublimate at extremely low temperatures. When these pristine comets first enter the inner solar system and begin to warm up, these super volatile ices erupt violently, producing enormous outbursts of gas and dust that can make the comet dramatically brighter than expected. Their tails are often spectacular, sometimes spanning tens of millions of kilometers, precisely because they still contain ices that have been locked in deep freeze since the solar system was young. This pristine composition tells us something important. These objects have been stored somewhere extraordinarily cold for an extraordinarily long time. Not just cold by human standards, but cold by the standards of outer space itself. Even in the Kuiper Belt, roughly 40 to 50 astronomical units from the sun, temperatures hover around minus 220 degrees Celsius. That is cold enough to preserve water ice and some other compounds. But to preserve the most volatile ices, the super volatiles like carbon monoxide and nitrogen ice, you need temperatures even colder, and you need the object to have remained at those temperatures for essentially the entire history of the solar system. That means the object has to have spent billions of years at distances far, far beyond the Kuiper Belt, deep in the outer solar system where the sun's warmth is effectively zero. The chemical composition of pristine long-period comets is physical evidence of long-term cold storage at extreme distances. Exactly what you would expect if these objects spent most of their existence sitting in the Oort Cloud, frozen and undisturbed, before a gravitational nudge sent them falling inward for the first, and possibly only time. The astronomer who assembled this argument most famously was a Dutch scientist named Jan Oort. In 1950, Oort published a landmark paper analysing the orbits of long-period comets. He was not the first person to suggest that a distant reservoir of comets might exist somewhere in the outer reaches of the solar system. An Estonian astronomer named Ernst Erpik had proposed something similar back in 1932. Erpik suggested that comets might originate from a vast cloud of objects lurking at the outermost edges of the sun's gravitational influence. But it was Oort who provided the detailed mathematical analysis of comet orbits that made the case truly compelling and gave the proposed structure the rigor it needed to be taken seriously by the scientific community. Oort studied the orbits of a sample of long-period comets, carefully calculating the key parameters of each orbit. One number mattered above all others. For each comet, Oort calculated the aphelion, the point in the orbit where the comet reaches its maximum distance from the sun. This is the farthest point the comet travels before gravity pulls it back inward, and it begins the long fall back toward the inner solar system. And when Oort looked at these aphelion distances, he found something striking. Many of the long-period comets had aphelia clustered at enormous distances from the sun, in the range of roughly 20,000 to 100,000 astronomical units. 1 astronomical unit is the distance from Earth to the sun, about 150 million kilometers. So 20,000 astronomical units is 20,000 times the distance from Earth to the sun. 100,000 astronomical units is 100,000 times that distance. These are staggering, almost incomprehensible numbers. For comparison, Neptune, the most distant known planet, orbits at about 30 astronomical units from the Sun. The farthest confirmed Kuiper Belt objects are a few hundred astronomical units away at most. The distances Oort was calculating were hundreds of times farther than anything in the known solar system. And those aphelia were not clustered in one direction. They were spread across the sky, pointing in every direction. Some pointed toward the northern sky. Others pointed toward the southern hemisphere. Some faced towards the constellation Virgo. Others aimed at Orion. The directions were random, uniformly distributed, exactly what you would expect if the comets were falling inward from a vast spherical cloud surrounding the Sun in every direction. Oort concluded that there must be an enormous reservoir of icy objects at these distances, forming a roughly spherical shell around the Sun. He estimated that this cloud might contain on the order of 100 billion objects, though he acknowledged the number was deeply uncertain. The cloud would be so far from the Sun that the objects within it would be only loosely held by the Sun's gravity. They would orbit incredibly slowly, each one taking millions of years to complete a single circuit. Most would remain in the cloud indefinitely, frozen, dark, and invisible, never approaching the inner solar system. But occasionally, something would disturb one of these objects, giving it a subtle gravitational nudge that changed its orbit and sent it falling inward toward the Sun. When that happened, the object would become a long-period comet, crossing the inner solar system in a matter of months, its ices vaporizing in the Sun's heat, producing a spectacular tail before heading back out into the darkness for another journey, lasting thousands or millions of years. This idea was elegant because it explained several observations at once. It explained where long-period comets come from. It explained why they arrive from all directions rather than from a preferred plane. It explained why their orbits are so elongated, stretching from the neighborhood of the Sun out to tens of thousands of astronomical units and back. And it explained something else that had puzzled astronomers for a long time. It explained why we keep seeing new long-period comets arriving century after century. If the reservoir contains hundreds of billions of objects, then even a very small rate of disturbance, just a tiny fraction of objects being nudged inward over millions of years, would be enough to supply the steady trickle of comets we observe. The supply is enormous, and the demand is small. The reservoir could sustain the observed comet rate for billions of years without running dry. Think about what that means. Humans have been recording comets for thousands of years. Ancient Chinese astronomers kept meticulous records of bright comets appearing in the sky, dating back more than 2,000 years. European astronomers began tracking comet orbits systematically in the 1600s and 1700s. And throughout all of recorded history, new long-period comets have continued to appear. They keep coming, one after another, arriving from different directions on orbits that take thousands or millions of years to complete. This means the source cannot be small or easily exhausted. It has to be immense, containing so many objects that even after 4.5 billion years of steadily leaking comets into the inner solar system, there are still plenty left. Some of the most spectacular comets in living memory have been long-period comets, visitors from the deep outer solar system that briefly dazzled observers before vanishing back into the void. Comet Hale-Bopp, which lit up the night sky in 1997, has an orbital period of roughly 2,500 years. It was visible to the naked eye for a record 18 months. Its orbit takes it far beyond the Kuiper Belt, though gravitational encounters with the giant planets may have shortened its original path considerably. Comet Hyakutakai, which appeared in 1996, passed remarkably close to Earth, coming within about 15 million kilometers of our planet. Its orbital period after that close encounter is estimated at roughly 70,000 years. That means the last time this comet visited the inner solar system, modern humans were living almost entirely in Africa and hadn't yet begun their great migration into Europe and Asia. Neanderthals still inhabited much of Europe. Agriculture had not been invented. Writing did not exist. And this comet was last here. It came from the deep outer solar system, swung past the sun, put on a breathtaking show with a tail stretching across half the sky, and is now heading back out into the darkness on a journey that will take 70,000 years to complete. Nobody alive today will ever see it again. Nobody alive for the next several hundred generations will see it again. Comet McNaught in 2007 became the brightest comet in over 40 years. So bright that observers in both hemispheres reported seeing it in broad daylight around the time of its closest approach to the Sun. Its orbit is so elongated that its period may stretch into the hundreds of thousands of years or longer. It arrived from the outer reaches, put on a performance that stunned astronomers and casual stargazers alike, and then disappeared back into the darkness. Each of these comets tells the same story. They come from far away. They arrive on orbits that are wildly elongated, swooping close to the Sun, and then heading back out to staggering distances. And they come from different directions, scattered randomly across the sky, consistent with a source that surrounds the Sun in every direction, rather than sitting in a flat plane. Now, you might wonder whether there could be some other explanation entirely. Maybe long-period comets do not come from a cloud at all. Maybe they are just random icy objects drifting through interstellar space that happen to pass through our solar system by coincidence. This is a reasonable question, and astronomers have examined it carefully. The answer is that the orbits of long-period comets rule this explanation out. If these comets were arriving from interstellar space, they would be traveling on hyperbolic orbits, trajectories that are not gravitationally bound to the Sun. They would fly through the solar system and keep going forever, never to return. But the vast majority of long-period comets are on elliptical orbits, meaning they are gravitationally bound to the Sun. They are part of our solar system. They belong here. They orbit the Sun, just on incredibly long timescales. Their orbits stretch out to enormous distances, but they are still closed loops, not one-way paths through the neighborhood. There is also the matter of orbital energy. When astronomers measure the energy of long-period comet orbits, they find that many of them are just barely bound to the Sun. Their orbits are so elongated, so stretched to the breaking point, that they are only marginally gravitationally attached to the solar system. A slight nudge outward would free them entirely, sending them drifting off into interstellar space. This is precisely what you would expect if these objects start in a distant reservoir where the Sun's gravity is incredibly weak. Out at tens of thousands of astronomical units, the Sun's gravitational grip is feeble. Objects there orbit so slowly and are held so loosely that the slightest disturbance can dramatically alter their trajectories. A tiny push inward, and the object begins a long, slow fall toward the sun, eventually appearing as a comet. A tiny push outward, and the object escapes the solar system altogether, never to return. This delicate balance between being bound and being unbound is a signature of the Oort Cloud. The long-period comets that reach us arrive with just barely enough gravitational energy to remain tied to the sun. They are on the edge. And this makes perfect sense because objects at such enormous distances are on the edge of the sun's influence. Anything farther out would not be orbiting the sun at all. The Oort Cloud, if it exists as proposed, marks the outermost frontier of what can still be called our solar system. Oort's 1950 paper established the foundation, but it also raised an immediate question. If this cloud of objects is real, what is disturbing them? What provides the subtle gravitational nudge that turns a dark, frozen, invisible chunk of ice into a brilliant comet visible from Earth? Oort himself proposed an answer. He suggested that passing stars could do it. Stars in our region of the Milky Way are not fixed in place. They drift through space on their own orbits around the galactic center, moving relative to the sun at speeds of tens of kilometers per second. Occasionally, a star passes within a light year or two of our solar system. When this happens, the star's gravity can tug on objects in the outer Oort cloud, altering their orbits just enough to send some of them tumbling inward toward the sun. Astronomers later realized that the gravity of the entire Milky Way galaxy also plays a role. A gentle but persistent force called galactic tides that slowly reshapes the orbits of distant objects over millions of years. These combined influences, passing stars and the gravitational pull of the galaxy itself, provide a natural and continuous mechanism for feeding comets from the Oort cloud into the inner solar system. And because these disturbances come from random directions, the comets they produce arrive on randomly oriented orbits, exactly matching what we observe. There is something almost poetic about this chain of evidence. We cannot see the Oort cloud. We cannot photograph it. We cannot visit it. It is too far, too dark, and too spread out. But every few years, one of its members arrives in the inner solar system, blazing with a spectacular tail of gas and dust. Visible to the naked eye, a brief and brilliant visitor from the outermost reaches of our sun's domain. Each long-period comet is a message from a place we have never seen, carried across tens of thousands of astronomical units of empty space, arriving after a journey that may have lasted millions of years. And when we study these messages carefully, when we trace the orbits backward to where they originated, they all point toward the same conclusion. Not toward one spot in the sky, but toward everywhere. Toward a vast, invisible, roughly spherical shell of frozen objects that surrounds everything we know about the solar system. The comets are the evidence. They are falling inward from the darkness, carrying with them the orbital signature of a structure so large and so distant that we may never see it directly, and yet their paths tell us it is there. The Oort cloud is invisible, but its fingerprints are written across every long-period comet that has ever graced our sky. Now that we understand what the comets are telling us, we need to step back and look at the bigger picture. Because the outer solar system is not one uniform emptiness stretching from Neptune to the stars. It is layered. It contains distinct populations of icy objects at different distances, each with its own characteristics, its own orbital behavior, and its own origin story. Understanding these layers matters because the Oort cloud is not the only collection of frozen bodies beyond the planets. There are several, and confusing them with each other makes it impossible to understand what the Oort Cloud actually is, why astronomers proposed it, and why some of these other regions do not serve as substitutes for the evidence it provides. Think of the outer solar system as a series of concentric zones, each one defined not merely by how far it sits from the Sun, but by the forces that shaped it. Closest to the planets is the Kuiper Belt. Beyond the classical Kuiper Belt is the scattered disk. Farther out still is a proposed region called the inner Oort Cloud, sometimes known as the Hills Cloud. And at the most extreme distances lies the outer Oort Cloud, the vast spherical shell that long-period comets have been pointing us toward for decades. Each zone represents a fundamentally different dynamical history. The objects in each region ended up where they are through different mechanisms, and tracing those mechanisms is central to the entire argument for the Oort Cloud's existence. Let us start with the Kuiper Belt, because it is the layer most people confuse with the Oort Cloud. The Kuiper Belt is a broad, relatively flat ring of icy bodies orbiting the Sun just beyond Neptune. It stretches from roughly 30 astronomical units to about 50 astronomical units from the Sun, a region that is distant by human standards, but practically next door compared to the Oort Cloud. The Kuiper Belt is not a hypothesis. It has been directly observed. Astronomers have detected and catalogued thousands of individual Kuiper Belt objects using ground-based and space-based telescopes. The first one beyond Pluto was discovered in 1992 by astronomers David Jewett and Jane Liu, an object designated 1992 QB1. That discovery confirmed what some researchers had been suspecting for decades: that Pluto was not a lonely outpost at the edge of the solar system, but rather the largest known member of a vast population of frozen worlds orbiting in the same region. Since then, the catalogue has grown enormously. We now know of several large Kuiper Belt objects that rival or approach Pluto in size. Eris, discovered in 2005, has a diameter slightly smaller than Pluto's, but is significantly more massive. Marke and Haumea are also substantial worlds, each more than 1,000 kilometers across, with their own moons and their own peculiar properties. Haumea spins so fast that it has been squeezed into an elongated shape, more like an egg than a sphere, and it has a faint ring of debris circling it. These are real, observed objects with measured sizes, known orbits, and confirmed physical characteristics. The Kuiper Belt is as real and as well documented as the asteroid belt between Mars and Jupiter. What makes the Kuiper Belt fundamentally different from the Oort Cloud is its shape. The Kuiper Belt is a disk. Its objects orbit the Sun in roughly the same plane as the planets. This flat structure is a direct legacy of the solar system's formation. The Sun and planets all condense from a flat, rotating disk of gas and dust 4.5 billion years ago, and the Kuiper Belt preserves that original geometry. Its objects never got thrown far enough from their original orbits to lose that disk-like arrangement. This flat geometry has an important consequence. When Kuiper Belt objects are disturbed and fall inward toward the Sun, they tend to arrive as short-period comets with orbits that stay relatively close to the plane of the planets. These comets orbit the Sun in fewer than 200 years, and their paths are roughly aligned with the ecliptic. This is completely different from the long-period comets we discussed earlier, which arrive from every direction. The Kuiper Belt cannot produce that random, spherical pattern of arrivals. Its geometry does not allow it. A disk sends objects inward along its own plane. Only a sphere sends objects inward from all directions. So the Kuiper Belt, well observed as it is, cannot be the source of long-period comets. Whatever reservoir is feeding those comets into the inner solar system must have a different shape entirely. Beyond the classical Kuiper Belt lies the scattered disk. This is a population of objects that tells a more violent story. Scattered disk objects were originally part of the Kuiper Belt's neighborhood, orbiting peacefully in the region beyond Neptune. But at some point in the solar system's history, they had close gravitational encounters with Neptune. The giant planet's gravity did not capture them or destroy them. Instead, it flung them outward onto wildly elongated orbits. A typical scattered disk object might swing as close as 30 or 35 astronomical units from the Sun on the near end of its orbit, dipping back into Neptune's neighborhood, and then travel out to several hundred astronomical units on the far end. These orbits are stretched, eccentric, and more tilted relative to the planetary plane than classical Kuiper Belt orbits. The key feature of scattered disk objects is that they remain dynamically connected to Neptune. Their closest approaches to the Sun still bring them near enough that Neptune's gravity continues to influence them, gradually altering their orbits over millions of years. They have not escaped Neptune's reach. They are like balls bouncing around a room where one wall keeps nudging them each time they come close. Their orbits are unstable on long time scales, precisely because Neptune keeps interacting with them. This is an important distinction. Scattered disk objects are not free from planetary influence. Their elongated orbits can be explained entirely by interactions with Neptune. They do not require any mysterious invisible structure to account for them. They are a natural byproduct of Neptune's gravity sculpting the outer solar system over billions of years. But here is where the picture becomes more interesting and more uncertain. Beyond the scattered disk, at distances where Neptune's gravity can no longer reach, astronomers believe there may exist another region. This is the inner Oort Cloud, sometimes called the Hills Cloud after the astronomer Jack Hills, who proposed its existence in a 1981 paper. The inner Oort Cloud is not something we have directly observed as a coherent structure. It is a theoretical prediction based on dynamical modeling and a small number of tantalizing observed objects that do not fit neatly into either the Kuiper Belt or the scattered disk. The inner Oort Cloud is proposed to occupy a vast zone stretching from roughly 2,000 to 20,000 astronomical units from the Sun. That is an enormous range. At 2,000 astronomical units, you are already far beyond the most distant confirmed Kuiper Belt objects. At 20,000 astronomical units, you are roughly a third of a light year from the Sun, an almost incomprehensible distance by solar system standards. Yet this entire region would still be closer to the Sun than the outer Oort Cloud, which may extend to 100,000 astronomical units or more. What distinguishes the inner Oort Cloud from the outer Oort Cloud is its predicted shape. While the outer Oort Cloud is expected to be roughly spherical, the inner Oort Cloud may be more flattened, retaining some of the disk-like geometry inherited from the original planetary disk. Objects in this zone were scattered outward by the giant planets, just as Oort Cloud objects were, but they did not travel quite as far. Because they remained at somewhat shorter distances, the external forces that reshape orbits at the most extreme distances, passing stars and the gravitational pull of the Milky Way, had less time and less leverage to randomize their orbital orientations. The result would be a population that is partly spherical and partly disk-like. a transitional zone between the flat structures near the planets and the fully spherical shell of the outer cloud. Some models suggest the inner Oort cloud may actually contain more objects than the outer cloud. This seems counterintuitive, but it makes sense when you think about the dynamics. Objects that were scattered to moderate distances, a few thousand astronomical units, could accumulate in a relatively dense reservoir because the sun's gravity is still strong enough there to hold them securely. Objects scattered to more extreme distances are held more loosely and are more vulnerable to being stripped away entirely by passing stars. So, the inner cloud, if it exists, may be a denser, more populated structure hidden between the observed solar system and the truly distant spherical shell. This brings us to the crucial question that ties all these layers together. Why is the outer Oort cloud expected to be spherical when everything closer to the Sun, the Kuiper Belt, the scattered disk, even the proposed inner Oort cloud, is flattened to some degree? The answer has everything to do with what happens to an orbit when it stretches far enough from the Sun. Remember that the solar system began as a flat disk. All the material that would eventually become planets, asteroids, and icy bodies started out orbiting in roughly the same plane. When the giant planets formed and began scattering small bodies outward, those bodies initially traveled on orbits that were elongated, but still oriented roughly along the original disk. They had been kicked outward, but their orbital planes had not yet been randomized. If nothing else had happened, the scattered objects would have formed a thick, but still disk-like cloud extending to enormous distances. But something else did happen. Once objects were scattered far enough from the Sun, they entered a regime where forces beyond the solar system itself became significant. Two forces in particular dominate out there. The first is the gravitational influence of passing stars. Our solar system drifts through the Milky Way alongside billions of other stars, and occasionally another star passes within a light year or two of the Sun. At distances of tens of thousands of astronomical units, a passing star can exert a gravitational pull comparable to or even stronger than the Sun's pull on those distant objects. Each stellar passage tugs on the objects, tilting their orbits, rotating their orbital planes, nudging them into new orientations. Over billions of years with thousands of stellar encounters, these gravitational tugs gradually randomize the orientations of the orbits. Objects that once all orbited near the same plane get scattered into every possible orientation, above the plane, below it, perpendicular to it, at every angle. The second force is galactic tides. This is the collective gravitational influence of the entire Milky Way galaxy, acting on objects at the Sun's outermost frontier. The galaxy is not a uniform sphere. It has a disk of stars, gas, and dust, and this disk exerts a tidal force, a stretching and squeezing effect, on objects orbiting the Sun at great distances. This galactic tidal force is extremely gentle, far too weak to notice at the distances of the planets or even the Kuiper Belt, but at tens of thousands of astronomical units, where the Sun's own gravity has become incredibly feeble, even a gentle external force can reshape an orbit over millions of years. The galactic tide preferentially rotates the orbital planes of distant objects, slowly tilting them away from the original disk and spreading them into a three-dimensional distribution. Together, passing stars and galactic tides accomplish something remarkable. They take a population of objects that started in a flat disk and transform it into a roughly spherical shell, but only at sufficiently large distances. Closer to the Sun, At the distances of the Kuiper Belt and scattered disk, the Sun's gravity dominates so thoroughly that external forces cannot effectively rotate the orbits. The disk stays flat. At moderate distances, in the proposed inner Oort cloud, external forces have some effect, but not enough to fully randomize the orbits. The structure becomes partially inflated, thicker than a disk, but not yet a sphere. And at the most extreme distances, beyond roughly 20,000 astronomical units, external forces have had billions of years to work on objects held only loosely by the Sun's feeble grip. The result is a fully randomized, roughly spherical distribution. The outer Oort cloud is spherical not because it formed that way, but because external forces reshaped it over billions of years. This is a beautifully self-consistent picture. The shape of each region in the outer solar system reflects the balance between internal solar gravity and external galactic forces at that particular distance. Close to the Sun, internal forces win and the structure is flat. Far from the Sun, external forces win and the structure is spherical. In between, you get something transitional. The layers are not arbitrary. They are a natural consequence of physics operating at different scales. Now let us talk about Sedna, because Sedna is one of the most fascinating objects in the entire solar system, and it sits right at the heart of the question about the inner Oort cloud. Sedna was discovered in 2003 by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz. It is a reddish, icy body roughly 1,000 kilometers across, making it a substantial object, though not as large as Pluto. What makes Sedna remarkable is not its size, but its orbit. Sedna's closest approach to the Sun, its perihelion, is about 76 astronomical units. That places it far beyond Neptune, which orbits at 30 astronomical units. But more importantly, it places Sedna far beyond the reach of Neptune's gravity. Neptune cannot be responsible for Sedna's orbit. The planet is simply too far away to exert any meaningful gravitational influence on an object whose closest approach is 76 astronomical units out. Scattered disk objects, by contrast, have perihelia of roughly 30 to 35 astronomical units, close enough for Neptune to keep tugging on them. Sedna is completely detached from any known planet's gravitational control. And then there is the far end of Sedna's orbit. Its aphelion, the most distant point, reaches nearly 1,000 astronomical units from the Sun. That is 20 times farther than the most distant, well-studied Kuiper Belt objects, and vastly beyond anything in the scattered disk. Sedna's orbital period is roughly 11,400 years. The last time Sedna was at its current position, human beings were just beginning to develop agriculture. The world's first cities would not be built for thousands of years. Sedna is sometimes described as a possible member of the inner Oort cloud, and its orbit does match some predictions for what inner cloud objects might look like. It is too far for the known planets to have placed it on its current path, but it is not far enough to have been fully randomized by external stellar and galactic forces. It sits in that intermediate zone where something else must have shaped its trajectory, but exactly what remains a subject of active research and debate. In 2014, another object with a similarly detached orbit was announced. Designated 2012 VP-113, this body has a perihelion of about 80 astronomical units, even farther from Neptune than Sedna's perihelion. Its aphelion reaches roughly 440 astronomical units, and its orbital period is about 4,200 years. Like Sedna, it orbits completely beyond Neptune's influence. Like Sedna, it raises the question of what force or mechanism placed it on such a distant, detached path. These objects are tantalizing. They hint that there may be a large population of similar bodies lurking in the zone between the scattered disk and the outer Oort cloud, too far for the planets to affect, but too close for external forces to have fully reshaped. If thousands or millions of such objects exist, they would constitute something very much like the inner Oort cloud that Jack Hills proposed. And finding even two objects with these peculiar detached orbits suggests that there must be many more, because the chances of discovering a rare, isolated object twice are very low. The fact that we found Sedna and 2012 VP113 implies that the population they belong to is large. But here is the crucial caveat, and it is important to state it clearly. Finding a handful of detached objects does not prove the entire Oort cloud exists. Sedna and 2012 VP113 may belong to the inner Oort cloud, or they may have arrived on their current orbits through some other mechanism entirely. Several explanations have been proposed. A passing star in the solar system's distant past could have gravitationally lifted their perihelia away from Neptune. The gravitational influence of nearby stars in the Sun's original birth cluster, the group of stars that formed alongside the Sun from the same cloud of gas, could have done something similar before those sibling stars drifted apart. Some researchers have explored whether an unseen distant planet might be responsible, though that hypothesis addresses a different set of orbital patterns and should not be conflated with the evidence for the Oort cloud itself. The point is that Sedna-like objects are clues, not proof. They strengthen the case that substantial populations exist in the deep outer solar system beyond Neptune's reach. But a handful of detached objects cannot tell us the size, extent, or total mass of a structure that may contain billions of members spread across tens of thousands of astronomical units. The clues point in the right direction, but they do not substitute for a complete picture that we have never been able to directly observe. What matters most about all these layers is what they tell us collectively about the history of the outer solar system. Each population, the Kuiper Belt, the scattered disk, the proposed inner Oort cloud, and the inferred outer Oort cloud represents the imprint of different forces acting at different distances over different timescales. The Kuiper Belt objects are the ones that survived relatively undisturbed in the flat disk beyond Neptune, never scattered far enough to lose their original orbits. The scattered disk objects are the ones Neptune kicked outward but kept on a leash, pulling them back periodically with its gravity. The inner Oort cloud, if it exists as predicted, would contain objects that Neptune expelled beyond its reach, but that remain close enough to the Sun that external forces have only partially reshaped their orbits. And the outer Oort cloud would hold the objects that were flung to the most extreme distances, where the gravity of the galaxy itself took over and randomized their paths into a sphere. These are not just 4 different distances. There are 4 different chapters in the same story, a story about how the solar system sorted its leftover building material after the planets formed. Understanding this sorting process is the key to understanding why astronomers believe in the Oort cloud. It is not enough to simply say that comets come from far away. You have to understand why the outer solar system has layers, why each layer has its own shape and orbital characteristics, and why the evidence for a spherical outer cloud is distinct from the evidence for anything closer. The Kuiper Belt is confirmed and observed. The scattered disk is confirmed and observed. The outer Oort cloud is inferred from comet orbits, but never directly seen. And the inner Oort cloud is suggested by objects like Sedna, and by models of how the solar system assembled itself. But it remains the least constrained of all four regions, a theoretical bridge connecting what we can see to what we believe must be there. The question that follows naturally from all of this is how the cloud was assembled in the first place, how trillions of small icy objects ended up on orbits stretching tens of thousands of times the distance from Earth to the Sun, scattered into a sphere by forces that reach far beyond our planetary neighborhood. To understand why astronomers believe the Oort cloud exists, it is not enough to observe what comets do today. You have to understand how those objects got out there in the first place. You have to rewind the clock 4.5 billion years back to the birth of the solar system itself, and trace the chain of events that could scatter trillions of small icy bodies into a vast spherical shell, stretching tens of thousands of times the distance from Earth to the Sun. This is the construction story of the Oort cloud, and it is one of the most physically compelling parts of the entire argument for its existence. The solar system formed from a collapsing cloud of gas and dust roughly 4.5 billion years ago. As this cloud contracted under its own gravity, it flattened into a spinning disk, with the young sun forming at the center. This protoplanetary disk contained everything that would eventually become the planets, moons, asteroids, comets, and all the other objects in the solar system. It was made mostly of hydrogen and helium, but it also contained heavier elements like carbon, nitrogen, oxygen, silicon, and iron, produced by earlier generations of stars that had lived and died before our sun was born. In the inner part of the disk, close to the young sun, temperatures were high. Only materials with high melting points, metals, and silicate rocks could survive as solid grains. These materials clumped together over millions of years, gradually building larger and larger bodies through collision and accumulation until they became what astronomers call planetesimals, objects roughly 1 to 100 kilometers across that were the building blocks of the rocky planets. Mercury, Venus, Earth, and Mars all assembled from these rocky planetesimals through billions of collisions over tens of millions of years. But farther from the sun, beyond what astronomers call the snow line, conditions were different. The snow line is the distance from the young sun where temperatures drop low enough for volatile compounds, water, methane, ammonia, carbon dioxide, to freeze into solid ice. Beyond this boundary, there was far more solid material available for building planetesimals because ice was abundant, and ice made up a substantial fraction of the disk's mass at those distances. The planetesimals that formed beyond the snow line were not dry rocks. They were mixtures of rock and ice, frozen composites that contained some of the most primitive material in the solar system. These icy planetesimals are the ancestors of today's comets. They are also the raw material from which the Oort cloud was built. The giant planets formed in this icy outer region. Jupiter, Saturn, Uranus, and Neptune all grew from cores of rock and ice that accumulated enough mass to begin pulling in enormous envelopes of gas from the surrounding disk. Jupiter, the largest, formed first and grew fastest, accumulating a core roughly 10 to 20 times the mass of Earth before its gravity became strong enough to sweep up vast quantities of hydrogen and helium from the disk. Saturn followed a similar path. Uranus and Neptune grew more slowly because they were farther from the Sun, where the disk was thinner and material was more spread out. They accumulated large icy cores but captured less gas than Jupiter and Saturn, which is why they're smaller and composed mostly of ice and rock, rather than hydrogen and helium. As these giant planets grew, they became gravitational bullies. Their immense gravity dominated the regions around them, and any small icy body that wandered too close to a giant planet experienced a powerful gravitational interaction. These encounters rarely destroyed the small body. Instead, they changed its orbit, often dramatically. A small icy planetesimal drifting peacefully on a nearly circular orbit could pass close to Jupiter and receive a gravitational kick that flung it onto a wildly elongated trajectory, sending it careening outward toward the distant reaches of the solar system. This process is called gravitational scattering, and it is the engine that built the Oort Cloud. Think of it as a gravitational slingshot operating in reverse. Space agencies use gravitational slingshots to accelerate spacecraft by flying a probe close to a planet so the planet's gravity boosts its speed. The same physics works on small icy bodies in the early solar system, except the result was not a carefully planned trajectory. It was a chaotic, random ejection outward into the deep solar system. Each giant planet contributed to this scattering process, but they did so in different ways. Jupiter, with its enormous mass, was the most powerful scatterer. Objects that encountered Jupiter received the strongest gravitational kicks. Many were kicked so hard that they exceeded the Sun's escape velocity and left the solar system entirely, flying off into interstellar space, never to return. Jupiter was efficient at removing material from the solar system, but it was almost too efficient. It ejected more objects than it retained. Many of the planetesimals scattered by Jupiter gained so much energy that they escaped the Sun's gravitational grip altogether. Saturn also scattered large numbers of icy bodies outward, though with somewhat less violence than Jupiter. Objects scattered by Saturn tended to end up on less extreme orbits than those scattered by Jupiter, partly because Saturn is less massive and delivers weaker gravitational kicks. Some of Saturn's scattered objects ended up on orbits stretching to thousands or tens of thousands of astronomical units, but still gravitationally bound to the Sun. But it was Uranus and Neptune that may have contributed the most to building the Oort Cloud itself. This seems paradoxical because Uranus and Neptune are much less massive than Jupiter or Saturn. Their gravitational kicks were weaker, but that weakness turned out to be an advantage. When a small icy body encountered Uranus or Neptune, it received a gentler kick, one that sent it outward onto an elongated orbit, but usually not with enough energy to escape the solar system entirely. The object would sail outward to enormous distances, tens of thousands of astronomical units, but remain gravitationally bound to the Sun. It would reach the far end of its orbit, slow down, and then begin the long fall back inward, eventually returning to the region near the planets where it might get scattered again. This is the sweet spot for building the Oort Cloud. You need to scatter objects far enough that they reach the extreme outer solar system, but not so far that they escape entirely. Jupiter was too powerful. It ejected too many objects completely. Uranus and Neptune were just right. They send objects outward to the distances where the Oort Cloud is expected to reside, roughly 10,000 to 100,000 astronomical units, while keeping them gravitationally bound to the Sun. Computer simulations of this process consistently show that Uranus and Neptune are the primary contributors to the Oort Cloud's population. Now, there is an important subtlety here that makes the whole construction process work. When a small body is first scattered outward by Neptune or Uranus, its orbit is extremely elongated. It swings out to maybe 50,000 astronomical units on the far end, but its closest approach to the Sun, its perihelion, still brings it back into the planetary region, maybe 20 or 30 astronomical units from the Sun. This means the object will keep returning to the neighborhood of the giant planets on every orbit. And every time it returns, it risks another gravitational encounter that could change its orbit again, perhaps ejecting it from the solar system entirely, or sending it crashing into a planet. If nothing intervened, most of these scattered objects would eventually be lost. Over millions of years, repeated encounters with the giant planets would either eject them from the solar system or send them plunging into the Sun or a planet. The Oort Cloud would never accumulate a stable population because objects would keep cycling through the danger zone near the planets, but something does intervene. And this is where the external forces we discussed earlier, passing stars and galactic tides, become not just interesting features of the Oort Cloud, but essential ingredients in its construction. When a scattered object reaches the far end of its orbit, out at tens of thousands of astronomical units, it spends a very long time there. Orbits are not like driving a car at constant speed. An object on an elongated orbit moves fastest when it is closest to the Sun and slowest when it is farthest away. At distances of 50,000 astronomical units, an object is crawling, barely moving relative to the Sun, hanging in the deep outer solar system for thousands or even millions of years before it begins to fall back inward. During this extended stay at extreme distances, the object is exposed to external gravitational forces. A passing star drifting through the solar neighborhood exerts a gentle tug. The tidal pull of the Milky Way's disk exerts a slow, persistent torque. These forces are too feeble to matter at the distances of the planets or even the Kuiper Belt, but out at tens of thousands of astronomical units, where the Sun's own gravity is extraordinarily weak, even a whisper of external force can reshape an orbit. Specifically, what these external forces do is lift the perihelion. They change the shape of the object's orbit so that its closest approach to the Sun moves outward, away from the planetary region. An object that originally had a perihelion of 25 astronomical units, bringing it back near Neptune on every orbit, might have its perihelion gradually raised to 500 or 2,000 or 10,000 astronomical units. Once this happens, the object no longer returns to the neighborhood of the giant planets. It has been detached from their gravitational influence. It is now permanently stored in the outer solar system, orbiting the Sun on an extremely distant path that never brings it close enough for any planet to disturb it again. This is how the Oort Cloud fills up. Planetary scattering provides the outward kick, sending objects to enormous distances. External forces then detach the objects from the planets by lifting their perihelia, locking them into stable, distant orbits, where they can remain for billions of years. Without the external forces, the objects would keep falling back to the planets and eventually be lost. Without the planetary scattering, the objects would never reach the distances where external forces can operate. Both ingredients are necessary. The Oort Cloud is a collaboration between the gravity of the giant planets and the gravity of the galaxy itself. This collaboration has a natural timescale. The process of scattering and perihelion lifting does not happen overnight. It unfolds over hundreds of millions of years. Computer simulations show that the Oort Cloud likely took several 100 million years to reach something resembling its current state, with the heaviest period of population occurring within the first billion years of the solar system's history. During this early period, the giant planets were still settling into their final orbits, the protoplanetary disk was still dissipating, and icy planetesimals were being scattered in enormous numbers. Billions of small icy bodies were flung outward by the giant planets. Most were lost, ejected from the solar system entirely by Jupiter's overwhelming gravity or destroyed in collisions or consumed by the sun. But a fraction, perhaps 5 to 10% of the original population, ended up trapped in the Oort Cloud. Their perihelia safely lifted beyond the reach of the planets by the gentle hands of passing stars and galactic tides. There is another factor that may have played a significant role in building the Oort Cloud, and it connects to a detail about the Sun's own birth that most people never consider. The Sun did not form alone. Stars almost never form in isolation. They form in clusters, groups of hundreds or thousands of stars condensing simultaneously from the same giant cloud of gas and dust. The Sun almost certainly formed in such a cluster, surrounded by sibling stars that were born from the same material at roughly the same time. In the first few 100 million years of the solar system's existence, the Sun was still embedded in this birth cluster. The other stars in the cluster were close, much closer than the nearest stars are today. Typical separations in a young star cluster might be only a fraction of a light year, compared to the 4.25 light years that currently separate us from Proxima Centauri. These nearby sibling stars would have exerted significant gravitational influence on objects scattered to the outer reaches of the young solar system. Some researchers believe that the Sun's birth cluster played a crucial role in shaping the inner Oort Cloud. Objects scattered outward by the giant planets would have encountered the gravitational fields of nearby cluster stars while they were at their most distant points. These interactions could have lifted perihelia very efficiently, detaching large numbers of objects from planetary influence and trapping them in the inner cloud at distances of 2,000 to 20,000 astronomical units. The cluster environment may have been particularly effective at populating this inner region, because the nearby stars provided stronger external perturbations than the more distant stars and galactic tides that dominate the outer cloud's evolution today. Eventually, the birth cluster dispersed. The sibling stars drifted apart over hundreds of millions of years, pulled away by galactic tidal forces and their own random motions. Today, those sibling stars are scattered across the Milky Way, indistinguishable from billions of others. But their gravitational legacy may survive in the structure of the inner Oort Cloud, a population of icy objects trapped in their orbits by stars that have long since wandered away. Once the birth cluster dispersed, the ongoing gravitational influences shifted to the two forces that dominate today: passing field stars, the random stars drifting through the galaxy on their own orbits, and galactic tides, the large-scale gravitational pull of the Milky Way's disk. These forces are weaker than the concentrated influence of the birth cluster, but they have been operating continuously for more than 4 billion years. Over that immense span of time, they have continued to slowly reshape the orbits of Oort Cloud objects, randomizing their orientations and maintaining the roughly spherical distribution of the outer cloud. Let us look more closely at how passing stars affect the Oort cloud today, because this process is not just historical, it is happening right now and it has measurable consequences. Stars in the Sun's neighborhood of the Milky Way are not stationary. They drift through space at typical velocities of 20 to 50 kilometers per second relative to the Sun. Over millions of years, different stars pass through the Sun's vicinity at different distances. Most pass far enough away that their gravitational influence on the Oort cloud is negligible, but occasionally a star passes within a light year or so of the Sun, close enough to exert a meaningful gravitational pull on objects at the most distant reaches of the Oort cloud. When this happens, the passing star's gravity perturbs the orbits of many Oort cloud objects simultaneously. Some objects have their perihelia lowered, pushed inward toward the inner solar system. These are the objects that eventually appear as long-period comets, falling inward from tens of thousands of astronomical units on trajectories that carry them past the Sun before sending them back out to the cloud. Other objects have their orbits disrupted in ways that push them farther out, potentially stripping them from the Sun's gravity entirely and sending them off into interstellar space. A single close stellar passage can produce what astronomers call a comet shower, a temporary increase in the rate of long-period comets entering the inner solar system that can last for millions of years after the encounter. We can even identify specific stars that will approach the Sun in the future. A star called Gliese 710, a small orange dwarf, roughly 60% of the Sun's mass, is currently about 63 light-years away, but moving toward us. In roughly 1,300,000 years, it is projected to pass within roughly 13,000 astronomical units of the Sun. That is close enough to pass through the outer Oort cloud itself, potentially displacing large numbers of objects and sending a wave of new comets toward the inner solar system. This will not happen for over 1 million years, so there is no immediate danger. But it illustrates that the Oort cloud is not a static, unchanging structure. It is constantly being stirred by gravitational interactions with passing stars, and those interactions are what keep the supply of long-period comets flowing. There is even evidence that a star passed very close to the solar system in the relatively recent past, astronomically speaking. Schultz's star, a small binary system consisting of a red dwarf and a brown dwarf companion, passed within roughly 52,000 astronomical units of the Sun about 70,000 years ago. That placed it within the outer Oort cloud. Modern humans were already alive at the time, living as hunter-gatherers during the last ice age. Schultz's star would have been far too faint to see with the naked eye, but its gravitational passage through the cloud may have dislodged objects that are still falling inward today, slowly making their way toward the inner solar system on journeys that will take hundreds of thousands or millions of years to complete. Galactic tides operate on a fundamentally different timescale and through a fundamentally different mechanism than passing stars, but they may ultimately be even more important for the Oort cloud's ongoing evolution. The concept of a galactic tide is difficult to visualize because it involves gravity operating on an enormous scale, the scale of the entire Milky Way. But the underlying principle is actually the same physics that creates ocean tides on Earth, just applied to a vastly larger system. On Earth, the moon's gravity pulls on the ocean nearest to it slightly more strongly than it pulls on Earth's center. And it pulls on Earth's center slightly more strongly than on the ocean farthest from it. This difference in gravitational pull across the width of the Earth, what physicists call a tidal force, is what creates the bulges of water on opposite sides of the planet that we experience as high and low tides. Now, imagine a similar effect operating not across the width of a planet, but across the width of a cometary orbit, stretching tens of thousands of astronomical units from the Sun. The Milky Way's mass is not distributed uniformly. Most of it is concentrated in a relatively flat disk of stars, gas, dust, and dark matter. The Sun orbits within this disk, and the disk's gravitational field is not perfectly even. The part of a distant comet's orbit that dips closer to the densest concentration of galactic mass feels a slightly stronger gravitational pull than the part that swings farther away. This tiny difference in pull across the enormous span of the orbit creates a tidal torque, a slow, twisting force that gradually changes the shape and orientation of the orbit over millions of years. Think of it this way. Imagine holding a very long, flexible rod horizontally in a room where gravity is slightly stronger on one side than the other. The rod would slowly bend, curving toward the side where gravity is stronger. The galactic tide does something similar to the orbit of a distant Oort Cloud object. It slowly warps the orbit, rotating its plane, changing its eccentricity, and over very long timescales, it can lower an object's perihelion from tens of thousands of astronomical units down to just a few, sending it on a path that carries it into the inner solar system where it appears as a comet. At planetary distances, this tidal force is laughably weak. The Sun's gravity dominates so completely that the galaxy's gentle pull has no measurable effect on anything orbiting within a few hundred astronomical units. But at distances of tens of thousands of astronomical units, where the Sun's gravitational grip has thinned to an almost imperceptible whisper, the galactic tide becomes a significant player. It is not strong in any absolute sense. It does not yank objects around or send them hurtling through space. It nudges, it whispers, it applies a patient, steady pressure that accumulates over millions and tens of millions of years. And given enough time, even the gentlest force can reshape an orbit completely. Unlike passing stars, which provide sudden, episodic jolts that happen randomly and unpredictably, the galactic tide is constant. It is always there, always operating, always applying the same slow torque to every distant orbit. Passing stars are like occasional gusts of wind that can scatter leaves in any direction. The galactic tide is like a steady, barely perceptible breeze that blows in the same direction day after day for millions of years. Over time, the breeze moves more material than any gust. Computer models indicate that galactic tides may actually be responsible for a larger fraction of the long-period comets we observe than individual stellar passages. The two mechanisms work together, with stellar encounters providing occasional sharp disturbances and galactic tides providing a constant background perturbation, but the tide's relentless persistence may give it the edge in total comet production over the long run. This combined picture, planetary scattering followed by external perturbation from stars and galaxy, is supported by sophisticated computer simulations that have been developed and refined over several decades. These simulations start with a model of the early solar system, a young sun surrounded by a disk of thousands or millions of icy planetesimals and 4 growing giant planets. The simulation then runs the physics forward in time, tracking every gravitational interaction between the planets, and the small bodies. It includes the effects of passing stars drawn from realistic models of the Sun's stellar neighborhood, and it includes the galactic tidal field calculated from models of the Milky Way's mass distribution. When these simulations are run, they consistently produce an Oort cloud. The giant planets scatter icy bodies outward. External forces lift the perihelia of the most distant objects, trapping them in a roughly spherical shell. The resulting cloud has properties that match what we infer from observations. It produces long-period comets at roughly the rate we observe. Those comets arrive from random directions, consistent with a spherical source. The orbits of the simulated comets match the orbital characteristics of real long-period comets. The models even reproduce subtler features, such as the clustering of original orbital energies near a specific value that Jan Oort first noticed in 1950. Some of the most influential simulations of Oort cloud formation have incorporated a dramatic chapter in the solar system's early history. A chapter that changed everything astronomers thought they knew about how the planets reached their current orbits. This is the model of early planetary migration known as the Nice model, named after the city of Nice in France, where it was first developed in 2005. For most of the 20th century, astronomers assumed the giant planets formed more or less where we find them today. Jupiter at roughly 5 astronomical units, Saturn at about 10, Uranus near 20, and Neptune around 30. The standard picture was one of orderly construction. Each planet grew from the material in its region of the protoplanetary disk and stayed put. The solar system was assembled neatly, like furniture placed in a room and never moved. The Nice model shattered that picture. It proposed that the giant planets originally formed in a much more compact configuration, all of them orbiting within a region stretching from roughly 5 to maybe 15 or 17 astronomical units from the Sun. Beyond the outermost giant planet lay a massive disk of icy planetesimals, billions of frozen bodies extending outward to perhaps 30 or 35 astronomical units. This disk contained a substantial fraction of the solar system's original solid material, perhaps 35 Earth masses or more of ice and rock. For hundreds of millions of years, the outer edge of this disk interacted gravitationally with Neptune, or rather with whichever planet occupied the outermost position at the time. Individual planetesimals drifted close to the outermost planet, received gravitational kicks, and were scattered inward or outward. Each interaction transferred a small amount of orbital energy and angular momentum between the planet and the planetesimal. The net effect, accumulated over millions of encounters, was that the outermost planet slowly migrated outward, pushed by the cumulative recoil of all those scattered objects, while Jupiter, absorbing some of the scattered material at the inner edge, drifted slightly inward. This slow migration continued for hundreds of millions of years, gradually spreading the giant planets apart. But then, something catastrophic happened. As Jupiter and Saturn migrated, they eventually crossed a critical orbital resonance, a configuration where Jupiter completed exactly 2 orbits for every 1 orbit of Saturn. When 2 massive planets lock into such a resonance, their gravitational interactions amplify dramatically. Each time they line up, they tug on each other in the same direction, reinforcing the disturbance rather than averaging it out. The effect is like pushing a child on a swing. Small pushes time to match the swing's natural period build up into enormous motion. The resonance crossing destabilized the entire outer solar system. Saturn's orbit became more elongated. This in turn destabilized Uranus and Neptune, whose orbits were disrupted violently. In some versions of the model, Uranus and Neptune actually switch places, with Neptune being flung outward past Uranus into the distant region it occupies today. The planet's orbits became temporarily chaotic, oscillating wildly, before eventually settling into their current configuration through a combination of gravitational damping and interactions with the remaining planetesimal disk. During this instability, the massive disk of icy planetesimals beyond the planets was torn apart. Neptune, surging outward into the disk, scattered icy bodies in every direction. Enormous numbers were flung inward, bombarding the inner solar system in a rain of comets and icy debris. This may explain what is known as the Late Heavy Bombardment, a proposed period roughly 3.8 to 4.1 billion years ago, when the Moon, Earth, and other inner solar system bodies may have experienced an intense spike in impacts. The cratered surfaces of the Moon and Mercury preserve a record of heavy bombardment in the solar system's early history. And while researchers continue to debate exactly how sharply impacts spiked during this era, the connection between planetary migration and a period of elevated bombardment remains one of the NEAS model's most compelling features. But many of those scattered objects were not flung inward. They were flung outward, sent careening into the deep outer solar system on enormously elongated orbits. This single event may have populated the Oort Cloud more rapidly and more heavily than any other episode in the solar system's history. The instability scattered so many objects so quickly that it essentially loaded the cloud in a geological instant. A burst of chaotic ejection that filled the outer solar system with icy debris in a few million years. The NEAS model and its more recent variants have been remarkably successful at explaining features of the solar system that were previously puzzling. They explain the orbital architecture of the giant planets, the structure of the Kuiper Belt, the distribution of Trojan asteroids sharing Jupiter's orbit, and the timing and intensity of the late heavy bombardment. The fact that these same models also produce an Oort cloud with properties matching what we infer from comet observations is powerful additional evidence that the cloud is a natural and expected outcome of the solar system's formation and violent early evolution. But it is important to be clear about what these simulations prove and what they do not. Simulations are powerful tools. They allow astronomers to test hypotheses, explore scenarios, and make predictions. When a simulation produces results that match real observations, it strengthens the case for the underlying model. But a simulation is not an observation. It is a mathematical experiment run on a computer. It tells you what should happen given certain assumptions about the physics and the initial conditions. If those assumptions are correct, the results are meaningful. If the assumptions are wrong or incomplete, the results may not reflect reality. The simulations of Oort cloud formation are built on well-tested physics. Gravity is well understood. Orbital mechanics is well understood. The properties of the Milky Way's gravitational field are reasonably well constrained. The initial conditions, a young solar system with a disk of icy bodies and 4 giant planets, are supported by observations of young star systems elsewhere in the galaxy. So the foundation is solid, but there are uncertainties. We do not know the exact initial distribution of icy planetesimals. We do not know the precise sequence of events during planetary migration. We do not know the exact characteristics of the Sun's birth cluster, or how long it took to disperse. These uncertainties mean that while the simulations consistently produce something resembling an Oort cloud, The details of that cloud, its exact population, its precise inner and outer boundaries, the total mass of material it contains, remain uncertain. What we can say with confidence is that the physics of planetary scattering and external perturbation naturally produces a distant, roughly spherical reservoir of icy objects around a star system like ours. This is not a speculative leap. It is a consequence of well-understood gravitational dynamics applied to realistic initial conditions. You start with planets and small icy bodies, let gravity do its work for 4.5 billion years, and you get an Oort cloud. The question is not whether the process works. The physics guarantees that it works. The question is how many objects ended up in the cloud, how far it extends, and what its detailed structure looks like. And those are questions we cannot yet answer with certainty because we have never seen the cloud directly. The construction story of the Oort cloud is ultimately a story about gravity operating at many different scales simultaneously. At the smallest scale, individual icy bodies interact gravitationally with the giant planets, receiving kicks that send them outward. At an intermediate scale, the sun's gravity holds these objects in enormously elongated orbits, keeping them tethered to the solar system even at distances of tens of thousands of astronomical units. At the larger scale, the gravity of passing stars and the entire Milky Way galaxy slowly reshapes those orbits, lifting perihelia, randomizing orientations, and occasionally sending objects back inward as comets. No single force builds the Oort cloud on its own. It takes the cooperation of gravity at planetary, stellar, and galactic scales, operating together over billions of years, to construct a structure that no telescope has ever seen, but that the laws of physics insist should be there. So we have laid out the evidence. Long-period comets arrive from every direction, pointing toward a distant spherical reservoir. The physics of planetary scattering explains how icy bodies could have been flung outward during the solar system's formation. Passing stars and galactic tides explain how those scattered objects were detached from planetary influence and locked into stable distant orbits. Computer simulations consistently reproduce a structure matching what we infer from comet observations. Every piece of the argument fits together with a logical coherence that is genuinely impressive. And yet, despite all of this, the Oort cloud has never been directly observed. No telescope has photographed it. No spacecraft has traveled anywhere near it. No individual object has been confirmed as belonging to the outer cloud while sitting at its full distance from the sun. Everything we think we know about the Oort cloud is built from indirect evidence, theoretical models, and inference. This is not a weakness. It is the nature of science at the frontier. But it does mean that enormous uncertainties remain. And it is important to be honest about what we do not know, because the gaps in our knowledge are just as scientifically interesting as the knowledge itself. Start with the most basic question. How many objects are in the Oort cloud? Nobody knows with any precision. Jan Oort's original 1950 estimate suggested roughly 100 billion objects. More recent models have produced numbers ranging from a few hundred billion to as many as 2 trillion or more, depending heavily on assumptions about the size distribution of the objects, which is itself almost entirely unknown. The reason is straightforward. We can only observe the comets that reach the inner solar system, a tiny fraction of the total population. From this trickle, astronomers try to work backward, estimating the reservoir needed to supply the observed rate of new long-period comets. But this calculation requires assumptions about how efficiently external forces dislodge objects, how many survive the inward journey without being ejected by the giant planets, and how many comets pass through undetected because they are too small or too faint. Each assumption introduces uncertainty, and those uncertainties compound, producing a final population estimate that could easily be off by a factor of 10 or more. The total mass of the Oort cloud is similarly uncertain. Early estimates suggested a total mass of a few Earth masses, meaning that if you gathered every object in the Oort cloud and compressed them into a single body, you would get something with the mass of a few Earths. More recent models suggest the mass might be somewhat higher, perhaps 5 to 20 Earth masses, but again, the uncertainty is enormous. Some researchers have argued that the Oort cloud might contain as little as 1 Earth mass. Others have suggested it could hold significantly more. The range of estimates spans more than an order of magnitude, which in scientific terms means we really do not have a firm handle on the number. This mass uncertainty matters because it connects directly to our understanding of the solar system's history. The Oort cloud was built from material that was originally in the protoplanetary disk, the same disk that formed the planets. If the Oort cloud is very massive, it means the early solar system contained more icy material than some models predict, which would have implications for how the giant planets formed and migrated. If the Oort cloud is relatively light, it places different constraints on those same processes. Getting the mass right would help us calibrate our models of solar system formation. But we cannot get it right without better data on the cloud's population, and we cannot get better population data without seeing the cloud directly. The inner and outer boundaries of the Oort cloud are also poorly constrained. The inner edge is typically placed at roughly 2,000 to 5,000 astronomical units. But this boundary is not sharp. It is a gradual transition whose exact distance depends on assumptions about stellar encounter history and the sun's birth environment. The outer edge is even more problematic. In principle, the cloud extends outward until the sun's gravity can no longer hold objects against the pull of the galaxy and passing stars, a limit falling at roughly 100,000 to 200,000 astronomical units. But this is a theoretical boundary. No observation has ever confirmed where the Oort cloud actually ends. Objects at the very outer fringe would be the most loosely bound, the most easily stripped away by external perturbations, and the most likely to have been lost over the solar system's lifetime. The outermost reaches of the cloud may have been significantly eroded over 4.5 billion years of stellar encounters, meaning the current outer boundary could be substantially closer than the theoretical maximum. There is also the question of structure within the cloud. Is the Oort cloud a smooth, uniform shell, or does it have clumps, voids, streams, and other irregularities? Computer simulations suggest that passing stars can create temporary concentrations of objects in certain regions of the cloud, channeling comets inward from preferred directions for millions of years after a particularly close encounter. If that is true, the comet flux we observe today might not be representative of the cloud as a whole. We might be seeing the aftermath of a specific stellar encounter rather than a steady-state average. This could bias our population estimates, making the cloud appear larger or smaller than it actually is, depending on whether we happen to be living during a period of elevated or reduced comet activity. All of these uncertainties stem from the same fundamental problem. we have never seen the Oort Cloud. We are inferring the properties of a vast structure from a tiny sample of objects that reach the inner solar system, like trying to estimate the size of an ocean by counting the fish that wash up on one small beach. The fish tell you the ocean exists. They tell you something about what lives in it, but they cannot tell you how deep it is, how wide it is, or exactly how many fish are swimming out there beyond the horizon. Could we ever observe the Oort Cloud directly? In principle, yes. In practice, it would be extraordinarily difficult. The individual objects in the cloud are small, dark, and incredibly far away. A typical Oort Cloud object might be a few kilometers across, reflecting only the faintest traces of sunlight at a distance of tens of thousands of astronomical units. At those distances, even the largest Oort Cloud objects would be many orders of magnitude fainter than the faintest objects detectable by current telescopes. The James Webb Space Telescope, the most powerful space observatory ever built, is designed to observe distant galaxies and faint stars. It could not detect a typical Oort Cloud object. Neither could any ground-based telescope currently in operation or under construction. Future survey telescopes like the Vera Rubin Observatory, expected to begin full operations in the coming years, will be able to detect many more Kuiper Belt objects and potentially discover additional Sedna-like bodies in the inner Oort Cloud region. But even the Vera Rubin Observatory, with its enormous mirror and wide-field camera designed to scan the entire visible sky every few nights, will not be able to image objects at the distances of the outer Oort Cloud. The objects are simply too faint. To detect an Oort Cloud object at 50,000 astronomical units, you would need a telescope far more powerful than anything currently planned. A telescope with sensitivity hundreds or thousands of times greater than anything that exists today. Sending a spacecraft to the Oort Cloud faces equally daunting challenges. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object, roughly 165 astronomical units from the Sun as of recent measurements. It has been traveling for nearly 50 years at about 17 kilometers per second. At that speed, Voyager would need over 2 centuries just to reach 1,000 astronomical units and close to 3,000 years to reach 10,000 astronomical units. To reach the heart of the outer Oort Cloud at 50,000 astronomical units, Voyager would need roughly 14,000 years. No human mission is going to wait 14,000 years for data. Even dramatically faster spacecraft, traveling at 10 or 20 times Voyager's speed, would take centuries or millennia to reach the outer cloud. The distances are simply too vast for any propulsion technology that currently exists or is likely to exist in the foreseeable future. So for now, and likely for a very long time to come, the Oort Cloud will remain indirectly observed. We will continue to study the comets it sends us. We will refine our models. We will discover more objects like Sedna that probe the inner boundary of the cloud. But the outer Oort Cloud itself will remain beyond the reach of direct observation, a structure whose existence we infer rather than confirm. And here is where it becomes important to step back and ask a broader question. Is there anything unusual about believing in a structure we have never directly observed? Is the Oort Cloud some special case in astronomy, an exception where scientists have abandoned their usual standards of evidence? The answer is emphatically no. Astronomers routinely infer the existence of unseen structures from their gravitational and orbital effects. In fact, Some of the most important discoveries in the history of astronomy have been made exactly this way, by noticing that something visible was behaving in a way that could only be explained by something invisible. The most famous example is the discovery of Neptune. In the early 1800s, astronomers noticed that Uranus was not following its predicted orbit. Something unseen was pulling it off course. In 1846, Urban Le Verrier calculated where an unseen planet would have to be to produce the observed deviations. He sent his predictions to the Berlin Observatory, and astronomer Johann Galle pointed a telescope at the predicted location and found Neptune within 1 degree of where it was supposed to be. Neptune was discovered not by scanning the sky and stumbling across it, but by inferring its existence from the gravitational effects it had on another planet. Sound familiar? The parallels with the Oort Cloud are striking. Long-period comets arrive on orbits that do not make sense unless a distant reservoir is supplying them. Neptune pulled Uranus off course in a way that did not make sense unless another planet was pulling on it. In both cases, the unseen structure was proposed because visible objects were behaving in ways that required an explanation, and in both cases, the proposed explanation was grounded in well-understood physics, specifically gravity. Dark matter provides an even more dramatic example. In the 1930s, astronomer Fritz Zwicky studied the Coma galaxy cluster and found that the galaxies within it were moving far too fast for the visible mass to hold the cluster together. The galaxies should have flown apart long ago. Zwicky concluded that unseen mass must be providing the extra gravity, mass that did not emit or reflect light, but still exerted gravitational force. Decades later, astronomer Vera Rubin and her colleagues measured the rotation speeds of spiral galaxies and found the same problem. Stars in the outer regions were orbiting far too fast for the visible mass to hold them. Something invisible was providing the extra gravity. Today we call that something dark matter, and we believe it makes up roughly 27% of the total mass and energy content of the universe. We have never directly detected a dark matter particle. We have never seen dark matter in a laboratory. We cannot photograph it. We cannot touch it. We infer its existence entirely from its gravitational effects on visible matter. And yet, the evidence for dark matter is considered overwhelming by the vast majority of physicists and astronomers. It is one of the foundational pillars of modern cosmology. Exoplanets provide yet another example. The first exoplanet orbiting a sun-like star, 51 Pegasi b, was discovered in 1995 by astronomers Michel Mayor and DDI Kalo. They did not photograph the planet. They could not see it at all. What they detected was a tiny wobble in the motion of the host star, caused by the gravitational pull of the orbiting planet. The planet itself was invisible, lost in the overwhelming glare of its star. But its gravitational effect on the star was measurable. From that wobble, Mayor and Kalo determined the planet's orbital period, its minimum mass, and its distance from the star, all without ever seeing the planet directly. This technique of radial velocity measurement, detecting planets through their gravitational influence rather than their light, has been used to discover hundreds of exoplanets. Many of these worlds have never been directly imaged. They're known only through the subtle effects they have on their host stars. The point of all these examples is that inferring the existence of unseen structures from their gravitational and dynamical effects is not unusual in astronomy. It is standard practice. It is how some of the most important discoveries in the history of science have been made. The Oort Cloud fits squarely within this tradition. We cannot see it, but the comets it sends toward us carry its gravitational signature as clearly as Neptune's gravity distorted the orbit of Uranus. The evidence is indirect, but it is real. It is grounded in well-understood physics, and it is consistent across multiple independent lines of reasoning. Let us count those lines of reasoning, because the Oort Cloud is not supported by a single observation or a single argument. It is supported by a convergence of evidence from several different directions, and that convergence is what makes the case compelling. First, the orbits of long-period comets. They arrive from every direction in the sky on extremely elongated orbits, with aphelia clustered at tens of thousands of astronomical units. The random distribution of arrival directions points to a spherical source, and the orbital energies indicate objects that are only marginally bound to the Sun, consistent with a distant reservoir at the edge of the Sun's gravitational influence. Second, the physics of planetary scattering. The giant planets, particularly Uranus and Neptune, naturally eject icy bodies outward during the process of planet formation. This is not speculation. It is a straightforward consequence of gravitational dynamics, confirmed by countless computer simulations. Third, the external perturbation mechanism. Passing stars and galactic tides can lift the perihelia of scattered objects, detaching them from planetary influence and trapping them in stable distant orbits. These same forces can also lower perihelia occasionally, sending objects back inward as long-period comets. This mechanism explains both how the cloud fills up and how it leaks comets into the inner solar system. Fourth, the consistency of computer simulations. Detailed simulations of solar system formation and evolution consistently produce Oort cloud-like structures with properties matching what we infer from observations. The simulated clouds produce comets at roughly the observed rate, with roughly the observed orbital characteristics, arriving from roughly random directions. Fifth, objects like Sedna and 2012 VP113, which occupy orbits consistent with the inner Oort cloud. These are not proof of the full cloud, but they demonstrate that detached populations exist beyond Neptune's gravitational reach, exactly where models predict the inner boundary of the cloud should be. No single line of evidence proves that Oort cloud exists beyond all doubt. The comet orbits could theoretically be explained by some other mechanism. The simulations could be based on incomplete assumptions. The Sedna-like objects could have arrived on their orbits through processes unrelated to the cloud. But the convergence of all these lines of evidence, pointing in the same direction, supporting the same conclusion, makes a powerful cumulative case. When 5 independent arguments all agree, the probability that they are all wrong in the same way becomes very small. This is how science works at its best. You build a case not from a single decisive observation, but from a web of interconnected evidence, each strand reinforcing the others. The Oort cloud's existence is supported by orbital data, formation physics, dynamical modeling, and analogies with well-established precedents in other areas of astronomy. The case is not proven in the mathematical sense. It is supported in the scientific sense, meaning that it is the best explanation consistent with all available evidence. What would it take to definitively confirm the Oort cloud? Ideally, direct detection of individual objects at Oort cloud distances while they are still out there, not after they have fallen inward and become comets. This would require telescopes far more sensitive than anything that exists today, or perhaps entirely new detection methods that have not yet been invented. Alternatively, a sufficiently large sample of Sedna-like objects could help constrain the inner cloud's properties. If astronomers discovered hundreds of detached objects with perihelia beyond Neptune's reach and mapped their orbital distributions in 3 dimensions, the resulting data could reveal the shape and extent of the inner cloud with far greater confidence than the handful of objects we have today. The Vera Rubin Observatory should help significantly with this second approach. Its ability to scan the sky systematically and detect faint, slow-moving objects will almost certainly yield new discoveries in the zone between the scattered disk and the inner Oort cloud. Each new detached object will add another data point to the emerging picture, but even the Vera Rubin Observatory will not see objects at the full distance of the outer cloud. That challenge may have to wait for a future generation of instruments. There is something deeply satisfying about the Oort cloud as a scientific concept. It represents science at its most elegant, a structure proposed not because someone happened to spot it through a telescope, but because the behavior of visible objects demanded an explanation. The comets pointed the way, the physics provided the mechanism, the simulations confirmed the plausibility, and the whole argument rests on the same kind of gravitational reasoning that has been the backbone of astronomy for centuries. The Oort cloud also reminds us of something important about the nature of knowledge. We often think of knowledge as seeing. We say we know something when we have observed it with our own eyes or at least seen a photograph. But much of what we know about the universe, we know indirectly. We know about the interior of the sun through models of nuclear fusion and observations of neutrinos. We know about the early universe through the cosmic microwave background, a faint glow of radiation left over from when the universe was only a few 100,000 years old. We know about the structure of atoms through experiments that measure how particles scatter off each other, not by opening an atom and looking inside. In every case, knowledge comes not from seeing the thing directly, but from interpreting the effects it produces on things we can see. The Oort cloud is invisible. It may always be invisible, but its effects are written across the night sky every time a long-period comet streaks into the inner solar system, trailing a tail of gas and dust, carrying with it the orbital signature of a place we have never seen and may never visit. Each comet is a message from the outermost reaches of the sun's domain, a frozen traveler that has spent millions of years drifting in darkness before a gentle gravitational nudge sent it falling toward the warmth of a star it could barely see. We know the Oort cloud exists not because we have seen it, but because the universe keeps sending us evidence that it is there. The comets arrive from every direction. Their orbits stretch to tens of thousands of astronomical units. The physics of planetary scattering explains how the objects got out there. External perturbations explain how they come back. Multiple independent lines of evidence all converge on the same conclusion. The Oort cloud is one of the largest structures associated with our solar system, a vast, roughly spherical shell of icy objects stretching nearly halfway to the nearest star. Its detailed structure, its exact population, its precise boundaries, and its total mass remain unknown. These are questions that future generations of astronomers will continue to work on, armed with better telescopes, more powerful computers, and perhaps entirely new methods of detection that we have not yet imagined. But the foundation is solid. The evidence is real. The reasoning is sound. And the conclusion, while not proven beyond all possible doubt, is supported by every line of evidence we currently possess. The Oort cloud has not been directly observed. But in science, Direct observation is not the only path to knowledge. Sometimes the most profound truths about the universe are revealed not by what we can see, but by what the things we can see are telling us about what we cannot. The comets have been delivering that message for billions of years, falling inward from the darkness, blazing briefly across our sky, and then vanishing back into the void. We only needed to listen carefully enough to understand what they were saying. And what they are saying is this: out there, far beyond the planets, far beyond the Kuiper Belt, far beyond anything a human spacecraft has ever reached, there is something vast and ancient and invisible. A frozen archive of the solar system's earliest history. A shell of ice and rock enclosing everything we have ever known, quietly orbiting in the darkness, waiting for a gravitational whisper to send the next messenger our way.